Hey there, we're going to go over some notes for accelerated motion. And before we jump into it, let's kind of talk about what causes an object's motion to change. Okay, so what causes object's motion to change? And the answer is when we have unbalanced forces. Now, our last unit that we just finished up, we had balance forces. Okay, if you remember, the balance forces were when an object was at rest or whenever it was moving at a constant velocity. But when we have unbalanced forces, an object's velocity will change. Okay, so those unbalanced forces will cause a change in velocity. And when we have a change in velocity, then we are now accelerating. Okay, the object is accelerating. And if I was to define acceleration, acceleration is the change in velocity over a period of time. And some examples of an object that's accelerating would be if an object is speeding up, if an object is slowing down, also if an object is changing direction. So this one is important here because a lot of times it's forgotten. So changing direction. An example of the changing direction would be if I'm moving at a constant velocity, if I'm driving a car, say 10 miles per hour at a constant rate, and I turn a corner, and if I stay going at a constant velocity, but I'm turning a corner, I'm changing direction. So I'm actually accelerating, even though I'm moving at a constant velocity because I'm changing direction. Okay, so direction is important because acceleration is a vector quantity. Now, from there, we can actually have or build an equation. Okay, so our basic equation for acceleration is an object's change in velocity, so delta v, over a period of time. And so that's the equation that we have to calculate our acceleration. Our velocity needs to be in meters per second. Time is in seconds. And so the unit for acceleration is then meters per second squared. And that's our basic equation that we use. Now we can sometimes expand that a little bit because we know now that to find the change in anything, it's final minus initial. So if I rewrote that, it would be acceleration is equal to my final velocity v minus my initial velocity v naught over a period of time. And so sometimes you might see this equation written this way, but it's the same thing. It's an object's change in velocity over time. And so if we look at a diagram on how we can represent an object that's accelerating, let's make a dot diagram. So let's say that I'm driving a car and it's got a steady oil leak and it leaves a pattern on the motion of the car. And so if the car is moving at a constant velocity, then my oil drips, right, if they're falling at a constant rate, then it would look something like this. So that's what my dot diagram would look like. But if the car was speeding up, then it would first kind of be close together, and then it would start to get larger and larger, the gap in between them, because it's speeding up, it's accelerating. And the other way we could look at it is if it's slowing down. So if that car is driving and it's slowing down, it might start out really far apart and then get closer and closer because it's slowing down. So that's a dot diagram that we could use to kind of represent it. Graphically, we have a few different ways we can look at it. So let's say we have a position time graph. So let's draw this. Oops. Let's say this is position, this is time. Now, last unit we seen position time graphs and they were linear lines. And so if you remember, that meant that it was a constant velocity. So if I have a linear line, that equaled constant velocity. And that was like our bowling ball lab. But when an object is accelerating, we end up with this parabolic nonlinear shape. Okay, so it could look something like this. So basically we have a curved line. Okay, so if it's curved, that means that the object is accelerating. Sometimes we have to straighten those lines, okay, and we call that graph straightening. And we'll get into that and we'll kind of practice that a little later. Now, some of the basic shapes that you do need to be familiar with is one, linear, right? So basically this linear graph, y is equal to x. So let's kind of draw this out here, right? They're directly proportional. And then for this parabolic shape, this would be y is equal to x squared. Another graph that you need to be familiar with, or shape I should say, is if we have a square root. So if it would look something like this. So y is proportional to the square root of x here. And then the last one that you do need to be familiar with is the inverse. So it looks something like this. And for this one, my y is proportional to 1 over x or 1 over x squared. So those are the different shapes that we're going to see in our class that you need to be familiar with. And then we're going to get into how we can also straighten those graphs as well. Now let's look at some examples of how I can use a velocity time graph to determine the acceleration of an object. So not a position time graph, but a velocity time graph. So let's say we have this graph here, and we make a best fit line, right? So it goes from here to here to here to here. Now, you might say, well, that's linear, so it should be constant. But remember, it's important to look at what we're graphing. Okay, we're graphing a velocity time graph. If this object was moving at a constant velocity, then it would be a straight graph, right? That means it's moving as time goes on, it's moving at a velocity of 4 meters per second the whole time. So that would be constant velocity. But we have a linear line here, so what that means is as time is going on, the velocity of the object is changing. And so we can determine the acceleration of this object with this velocity time graph. Kind of similar to how we found the velocity of an object with the position time graph. Okay, so we're going to pick a couple points. So let's say we pick this one here and this one here. Okay, so this point is 0, 1. Up here we have 2, 5. And let's find the slope of this line. So remember, slope is equal to your change in y over your change in x. So that gives me y2 minus y1 all over x2 minus x1. So using those data points, that would give me 5 minus 1 on the top all over, on the bottom we would have 2 minus 0. Okay, so that's going to end up being 4 over 2, but let's include our units here, right? Because we're in physics. So the 4, right, that's my y, and if you look at the units, it's meters per second. So 4 meters per second. And for the 2, for the x-axis, we're graphing seconds. So over 2 seconds. And so the answer here for the slope it's equal to 2 meters per second squared. And if you remember from our equation, that is the unit for acceleration. So my acceleration is equal to 2 meters per second squared. Now, let's look at this and kind of see where that came from. So remember, the slope was equal to change in y over change in x. And if we replace our y variable with what we're graphing here, which is velocity, then it would be change in velocity. And on the x-axis, we're graphing time. So over time, delta v over delta t. And going back up here, that was my equation for acceleration. So finding the slope of a velocity time graph will tell me what the object's acceleration is. And so that's why if we look at the slope of this line up here, this linear line, it's constant, right? Or it's zero, so you have zero acceleration. All right, so let's look at another thing we can do with these velocity time graphs. We can actually use a velocity time graph to determine the displacement of an object. And so to do this, we're going to use another trick. Okay, we're going to find the area underneath the curve. So let's say, for instance, the question is, what is the displacement of this object after, let's go 2 seconds. And so we have a velocity time graph. We're looking for this displacement, or my delta x. And so what we're going to do here is we're going to find the area underneath the curve of this line between our x-axis and the line. So if I make a straight line right here, and I make another one right here, I'm building a triangle and a rectangle because I know how to find the area of those two shapes. So you always want to break it up into some shapes that we're familiar with working with. So here we have this triangle here, and remember the area of a triangle is equal to 1/2 base times height. And so for this triangle, my base is from 0 to 2 seconds, and my height is from 1 meter per second to 5 meters per second. So that would give me 1/2 times the base, which we said was 2 seconds, times the height, which is from 5 to 1, so that's going to be 4 meters per second. Now look what happens to my units. I have seconds times meters per second, so the seconds will cancel out. So 1/2 times 2 times 4 is equal to 4 meters. So there's the area of this triangle here. Now let's find the area of this rectangle, which is, and you should remember, area is just equal to the length times the width, right? Base times height or length times width. And so looking at this, my base here, or the length, you have 2 seconds from 0 to 2. And the height that goes from 0 to 1 meter per second. So 1 meter over seconds. And again, my seconds will cancel out, and that's equal to 2 meters. So the area here is 2 meters. So for the object's displacement, your delta x is going to equal the area under the curve. So we just add those up. So it's going to be 4 meters plus 2 meters, which is equal to 6 meters. So when we have a velocity time graph, we can find the area under the curve, and that will tell me the object's displacement. So let's kind of look at that and see what's happening. So what we're doing is we're taking the velocity and we're multiplying the velocity by time. Right? We're taking our y-axis and we're multiplying it by our x-axis. And if you remember from the last unit or from the beginning of the year, we had an equation. We had an equation where the velocity was equal to the displacement over time. If we rearrange this equation and I multiply both sides by the delta t, what you end up with is your delta x is equal to v delta t, which is what we're doing here. Okay, we're taking the velocity, we're multiplying it by the time, and we're solving for the displacement. Okay, so that's another trick we can do with these graphs. We can find the slope of the velocity time graph to find the acceleration, and we can find the area under the curve to find the displacement. Now, one thing that you do need to keep in mind is if, let's say I have a graph, a velocity time graph. So this is velocity in meters per second, and this is time in seconds. And let's say that the shape of it goes from here to here, and then it goes from here to here, where it dips down into that negative quadrant. So if I'm trying to find the displacement, and let's say this is 5 seconds. So after 5 seconds, I wanted to find the displacement. Again, you just find the area between the x-axis and your graph. So we would have this shape here. Okay, we got a square there. We have a small triangle here. But we also have a triangle here. And so when that happens, you need to make sure you keep this negative. So your area would be the area, or your displacement would equal the area of the square plus the area of this triangle minus the area of this triangle, because that one is negative. Okay, all this other stuff, all this other area over here and here, we're not worried about. All we're worried about is the area between the line, okay, the graph, and your x-axis. Okay, and that will tell me what my displacement is.